俾個問題 Simon 只會俾更加。
So now we are in the chapter heat transfer. In this chapter, we will learn some knowledge to solve, maybe should say, to answer the above questions. Heat transfer is that energy in transition due to a temperature difference. That means that if there is a temperature gradient in the system, heat transfer will take place. So, the knowledge of the temperature distribution in the system is very important. In this chapter, we will use Q dot to represent the heat transfer. Actually, it is a heat transfer rate. The unit should be watt or joule per second. Sometimes we may use kilowatt. That should be kilojoule per second. We use this item to denote the heat transfer in this chapter. When we talk about the heat transfer, there are three basic mechanisms: conduction, convection, and radiation. Conduction in Chinese, it should be 传导. Convection, 对流. Radiation, 辐射. 热传导, 热对流, and 热辐射. We only have these mechanisms in heat transfer. So, let's go through them. Here, I give you a situation. We may have some firewood. We'd like to use this firewood to burn a fire for us. So, if you use your hands to touch the firewood at this end, you will feel it warm, right? Oops, sorry. Why? Because the conductive heat transfer by this firewood. We have a temperature difference. At this end, we have higher temperature. At this end, we have a lower temperature. Due to this temperature differential, conduction happens inside this firewood. So that is conduction. If you put your hand at the top of this fire, you can feel the hot air flow through your hand. You feel such hot that you move your hand away directly, immediately. Why? Because your hand are heated by the moving air with very high temperature via convective heat transfer. Moving hot air heat your hand. This is convection. If you stand away from the fire, maybe you stand here, the distance is far away enough so that you can neither feel the conductive heat transfer from the fair and the fair wood, nor feel the convective heat transfer by the hot air, the burned air. But you can still feel warm. Why? That is a radiation heat transfer. You can absorb the radiative heat energy from the fire. That is radiation. These are the three mechanisms. Now, let's go through these three types one by one. First, conduction. Conduction, sometimes we call it a conductive heat transfer. In essential, it is a heat transfer due to the interaction of atoms or molecules. For fluid and solid, the mechanism for conduction are different. For a fluid, let me explain more. Maybe first conduction, okay? I maybe show you a sketch. Let's say we have a solid. This is a solid, maybe a plane, maybe a plate. At this surface, we have a temperature T1. At this surface, we have a temperature T2. Maybe the temperature T1, let's say, is larger than T2. So what we have is we have the heat transfer along this solid. So that is a conduction. And for a fluid, the conduction is caused by the direct impact between the molecules. According to the kinetic theory of gas and fluid, we have very irregular form of molecules, right? Very irregular with different velocity. These molecules keep moving around with different velocity. They are all hitting into one another, colliding and exchanging the momentum with each other, during the conduction process. So the conduction inside a fluid is due to the clearance of the molecules. Conduction, in essential, is the heat energy transfer via the clearance between different molecules. But in a solid, it is not the case. In a solid, we have a much more regular much more regular form for molecules. They are connected together by this lattice. The connection between these molecules, we call it a lattice. The conduction happens in the solid. Have two methods to approach. First, by the lattice vibration. Second, the drift of free electrons. Vibrations. It is where the connections between all the molecules are vibrating, and Now we have that kind of wave go through. This is a vibration. Also, in a solid, we always have these free electrons spinning around, and these free electrons can move through the solid and provide a form of an energy exchange. So in a solid, conduction happens by two approaches. First, vibration of molecules. Two, the drift of free electrons. Actually, we have the definition of the thermal conductor and the thermal isolator. Thermal conductor have the both method for a solid. It can the conduction can happen through the vibration of the molecules and the drift of free electrons. Because in this kind of in the thermal conductor, there are more free electrons than the thermal isolators. So thermal isolators is the material that can only transfer the conduction by the vibration of molecules. This kind of material has much less free electrons than the conductor. So actually, if we have a material which is a good thermal conductor, it always a good electricity conductor because it has lots of free electrons. Here you should pay attention. Conductions can happen inside a solid and a fluid. When we say fluid, that should be a liquid and a gas, right? But the material that quite often conduction applies to is solid. Although you can have it in other form, but solid are usually the one that we are dealing with. So usually we are dealing with the solid. And then you should pay attention here. When we're talking about the conduction in a fluid, first thing is that there is no macroscopic movement. There is no macroscopic moment because especially for a fluid. Because if a macroscopic motion of a fluid is involved, we will have another heat transfer. That should be convective heat transfer. So convection, first thing, convection can only happen in a fluid because the macroscopic motion of fluid is involved in convection. Then there should be a fluid and solid interface. That is convection. I may use a simple example. Let's say we have a solid surface, this is a solid, and in convection, what we have is a moving fluid. Let's say the temperature is T∞. The temperature at this surface is TW. The surface can be cooler than the fluid, or hotter than the fluid. In this case, let's say TW, the solid is hotter than the fluid, so TW larger than T-finity. What we will have is we have the heat. Heat will flow from the solid into the fluid. This is convection, convective heat transfer. Actually, this fluid is heated by this solid. Convective heat transfer happens at this interface. So in essential, convective heat transfer is the energy exchange between the surface, should be a solid and a fluid, which moves over the surface. This should be convective. Here, you should pay attention. Convection involves the macroscopic motion. That means convective heat transfer definitely involves fluid mechanics, right? Because we have the movement of fluid. So we may say convection is a combination of heat and mass transfer. Because without mass transfer, convection cannot happen. Let's say there is again a hot surface. The fluid mass will absorb heat from this hot surface. Then this heated fluid mass with heat is driven to a cold region by a force. What we have? Heat transfer and mass transfer, right? The movement of fluid. So convection is difficult to solve because we combine two things together, heat transfer and mass transfer. Convection, direct movement of macroscopic part from a hot to a cool region of a fluid. So that fluid involved, the movement of fluid involved, while the heat transfer involved. Because we have the movement, that means we must have a driving force, because movement is provided by the driving force. So according to different driving force, convection can be classified into three types: forced convection, natural convection, and mixed convection, depending on different driving force. Forced convection. The driving force is the external force. That means the fluid flow is driven by a mechanical means, like the electrical fan. If we have a big electrical fan, here we have a hot sphere. The flow driven by the electric fan, we have this kind of flow around this hot sphere. That is a forced convection. The driving force is external force. Natural convection. Sometimes we call it is free convection. Free convection, natural convection, they are the same. That means the fluid flow is driven only by the buoyancy force without any external force. Buoyancy force is induced by the density difference as a result of the temperature change. You should know this, right? We have different change. And then we have the density difference. That is the natural convection. The driving force is buoyancy force only. So if we have a hot sphere, the temperature of the sphere is higher than the surrounding air. So due to the buoyancy force, we have such airflow. This is a natural convection. Mixed convection. Obviously, it is a combination of forced convection and natural convection. When these two are comparable, let's say if we use a smaller fan, the flow, the airflow will be like this. The effect of the external force and the buoyancy force are comparable. That is a mixed convection. At this point, any problems? Sometimes full-time students ask for additional explanation in Chinese. If you need, please let me know, okay? If you cannot understand or need more explanation, please feel free to let me know, okay? For the conduction, convection, any problems? Yes, but here I will actually remind you again. When we say conduction, yes, it can happen inside solid and liquid. Solid and fluid, but usually we are dealing with the conduction in a solid. Okay. And what's wrong?浮力. Sometimes we call it 浮力 or 浮升力. Notice? You guys do not know buoyancy force? Okay. 浮力 Yes. 它是因为那个不同的那个密度嘛，比如在空气中，空气密度不同，它就会有浮力。然后又由于 temperature difference， 它会造成那个密度差，然后就会造成这个 buoyancy force。应该我们是在高中的 physics 会学那个水里面的浮力，就球嘛，你游泳的时候你可以浮在水面上嘛，那也是浮力嘛，对吧？原理是不一样的，但我们都喊它是个浮力，就是能把你托起来的力气。不给你们那个不讲太多了，会混乱。反正这里就是浮力，是由于温度的改变，然后造成了 temperature change， 然后导致了 induce， 然后的 density difference， 然后就会产生了这个 buoyancy force。OK， 可以吗？如果你加热水或加热空气，你会发现它往上走。比如说，很简单，就是你看到那个一个板子嘛，我们去加热它，然后你又看到，最简单的就是刚才这个例子嘛。你把手放在火上，你会感觉到那个空气是往上升嘛，对吧？就是那个它为什么会往上升，就是因为有了，对吧 ？buoyancy force。 Up to now, it's okay? Okay, buoyancy force. So convection, you should remember it is a combustion of heat and mass transfer. It is involved, it can only happen in the liquid because the macroscopic motion of a fluid is involved in the convection. This is the convective heat transfer. The last one is a radiation. Radiation, in fact, we have a matter or a object. If the temperature is larger than the absolute zero, it will emit radiation. In other words, each matter will emit radiation. But when we say the radiation heat transfer, or I should say the radiation actually in essential, it is electromagnetic wave. In essential, it is the electromagnetic wave. In Chinese 就是电磁波，波是一种波 which is characterized by the wavelengths. Basically, there are a large range for this radiation. But when we talk about the radiation heat energy, heat transfer, we only covers a small range that we call this radiation as the thermal radiation, because only the radiation in this range can give us the heating effect when it is incidenting upon the absorber. Only in this range, it can have the thermal effect, the heating effect. The range is from 0.1 micron to the 100 micron. Actually, it covers the infrared, visible, and a part of the ultraviolet. That should be, maybe I can show you better. So this is 100, this is 10, this is 1.0, and this is 0.1. So this is micron. Okay, and this range is we call the thermal radiation. Thermal radiation. From here, it should be UV. 紫外线 UV. Okay, from here to maybe here, it should the visible part, the visible spectrum. 可见光 spectrum 就是那个频谱，你们应该知道这个词吧？ From here to, I think it should be all the way to this one. Yes, that would be IR, 红外线. And from here should be microwave, right? So for the radiation, we only covers this part, covers this spectrum. This is thermal radiation. Oops, sorry. And for the solar energy is quite important, right? If without solar energy, there is nothing in our planet. There will be nothing, right? So solar should be, where's my pointer? Yes, here. Huh? Yes. So it's from 0.3 micron to about 3. This is a solar. Okay, solar radiation, the spectrum for solar radiation. And also, let's say we have sun, right? This is a sun, and this is our Earth. Sun is about 3,000 K, the temperature should be. Our Earth maybe, let's say, about 300 K, 310 K. So, Sun, the temperature is larger than this absolute zero. So, it will definitely emit radiation, right? At this time, our Earth will be an absorber. That is absorb this kind of radiation heat. But in turn, our Earth, the temperature is larger than this than absolute zero. It will also emit radiation. Now, Sun becomes an absorber. It will absorb the radiation from our Earth. That means each object will emit radiation. And another point is that radiation is the only heat transfer which can be happened through the vacuum. 真空中它是唯一的一个 mechanism， 它不需要radiation do not need any media， 在真空中就可以进行，因为 actually 这里太阳和地球之间都是真空嘛，就是这样过来，太阳会发射会做 radiation， 地球 Earth 会吸收它的 radiation， 反过来，因为地球的 temperature 也是大于 absolute zero 的，它也会 radiation， 就是 emit radiation， Sun 呢也会接受 radiation， 所以 so radiation is not easy to solve because each object is absorber, is an emitter, right? So it is not easy to solve the radiation. Okay. Up to now, for the three mechanisms, conduction, convection, and radiation, any problems? For the mechanisms of radiation, convection, conduction. If no, I will continue. Okay, first, let's have a look at the conduction heat transfer. First, I will introduce to you the Fourier law, which is used to solve the conductive heat transfer. Then we will use this equation to calculate the conductive heat transfer through a single or multiple layers of object. Then we will use the electrical analogy to make the calculation easier. At last, we will try to solve the conduction system with convection boundaries. First, we assume we have the one-dimensional and steady-state conduction. one-dimensional. That means within the system, the temperature gradient only exists along one direction. Usually we use X direction. That should be sometimes we call it isothermal along X direction. We only have the conduction heat transfer along one direction. Steady state. You have learned fluid mechanics in the last semester, so you should know the words steady. That means the property do not change with time. So here is the temperature do not vary with time. That is the assumption of one-dimensional and steady state conduction. That's the assumption before we perform the analysis. One-dimensional means we have one direction temperature gradient. Steady, do not vary with time. Next, Fourier's law of heat conduction. We use this law to solve the conduction heat transfer, to calculate the heat transfer rate during conduction. So in the if we have the temperature change in the X direction, that means we may have a plane or plate. The Fourier's law should be this equation. If we have like a pipe, a cylinder, we will use the equation here, this one. If you look at these two equations, Q dot is the heat rate, heat transfer rate. A is the surface area, which is normal to the heat flow. That should be, if we say X direction, that should be YZ, right? The YZ plane. dt over dx or dt over dr. Actually, it is the temperature gradient along the X direction or the R direction. Here we have an important parameter, that is K. That is the thermal conductivity of material. Actually, it is a material property. For heat rate, I have already told you, we will use watt as its unit. That should be joule per second, right? And the area, the unit should meter square. For this temperature gradient, it should be, right, K per meter. We have the unit for K. That should be that we have the unit should be watt over meter times K. Here should pay attention, we have a negative sign because dt over dx or dr is negative. Negative because heat can only flow from the high temperature to low temperature, flow down the temperature gradient. So dt over dx or dr is a negative value. So here we have a negative sign. That's the Fourier laws to calculate heat conduction. Okay, thermal conductivity. As I said, it is a material property. The conduction through a material is directly proportional to K, thermal conductivity. So, if material with a good thermal conductivity, it's a thermal conductor. Otherwise, material with a poor thermal conductivity is a thermal isolator. Remember that? I told you thermal conductor usually is a good electricity conductor because thermal conductor use both the vibration and the free electrons. It have much more free electrons than the thermal isolator. Well, the thermal isolator has much less free electrons, so during the conduction, it can only transfer energy by vibrating. It has not enough free electrons to help it transfer energy. So it is a thermal isolator. Usually, it is a poor electric conductor because of less free electrons. Thermal conductivity of a material it depends on several parameters, on several properties. It is affected by the temperature, phase, and the structure of material. Here, I don't want to talk too much about it, but I need to remind you that in a real application, we usually assume K is constant, especially when the temperature range under consideration is not too large. We usually assume K is constant because I taught you that we usually dealing with solid in conduction. So we usually assume K is constant. Now, let's use the Fourier law to solve the conduction problem. First, in front of us, it is a plane. It is a solid, a slab. It has a constant surface area, which is normal to the heat transfer because we assume the one-dimensional steady-state conduction. So the conduction will happen in the x direction. It has a constant surface area, normal to x direction. At this side, at this surface, it has a temperature of T1, while at this side, it has a temperature of T2. In this case, we assume T1 is larger than T2. This material has a thermal conductivity K. As I said, we assume it is constant for this solid. So let's apply the Fourier's law. Sorry. That should be Q dot. The conductive heat transfer equals to minus K area times area dt over dx. Okay, thank you. This is the Fourier's law to solve this problem. Here we assume Q dot K and the area is constant or constant. We assume the heat transfer rate, the thermal conductivity, and the area are constant. Q is constant because we assume it's a steady state. K is thermal conductivity, constant. Area, constant. So we can rearrange our equation. That should be dx, right? Integral. Oops. Since Q, K, A are constant, we can take them outside from the integral. From surface 1 to surface 2, right? That should be x minus 0. Right? If we rearrange x, so we have a linear temperature profile through this wall. Linear temperature profile, or maybe linear temperature distribution through this wall. This is the equations to calculate the conduction through this wall with a temperature difference. So you should remember it, okay? You should know how to solve this problem. Up to now. Any problems? If no, I will continue. Okay. If we have a hollow cylinder, maybe we you can call it a circular pipe. What we have is an inner face of this pipe. At a higher temperature, while its outer surface have a lower temperature. Due to this temperature differential, we definitely have a conduction through this pipe wall, right? So according to the Fourier's law, what we have is Q dot, the conduction heat transfer, equals to, this is a Fourier's law, right? But here you should pay attention. Area is no longer constant. The normal area is changing with its radius, right? So it equals to times the length times the length. So area is no longer constant. What we have is we plug the calculation of area into this equation. So this time, we need to have right? Integral we should R1 to R2 from T1 to T2. Again, we assume Q dot and the conductivity are constant. So we can take them out. For this, ln T2 minus T1, right? Do you know this one? The integration. Yes, integration. We have ln R2 over R1. Okay, the integration. So if we rearrange this, we can get the conduction heat transfer through this circular pipe. That should be right. Up at this point, any problems? If no, I will continue. Any problems? If no, I will continue. Here, I should remind you for those equations, equations to calculate the conduction heat transfer through this circular pipe or the plain slab, you should become familiar with this equation, because later we will use them quite often. Okay. Okay, here we have known how to calculate the conductive heat transfer through a single material, through a single layer. But how about we have a multiple layer? Let's say we have 3 slabs. This slab is made by 3 different materials. So we have 3 different conductivities, K1, K2, and K3. Here we assume we have a constant area. And we have 3 different thickness or displacement. The X displacement. We have 3 different thickness and 3 different conductivities for 3 different material. So if we want to know the conduction through this composite, how should we do? Again, here, first you should have the basic understanding, that is the conduction, the conduction heat transfer rate through these 3 different materials is the same, is constant. Through the whole system, the conduction heat transfer rate is constant. So by using this equation, from surface 1 to surface 2 equals T1 minus T2 over X1 over the thickness, right? Conduction heat transfer keeps constant, so that it equals, T3 X2. It also equals to K3 through the third layer area divided by the thickness. Thus is how we calculate the conduction heat transfer through a multiple layer with 3 different materials. We assume the area is constant. So now the equation becomes like this. If we rearrange this equation, we rearrange it like this. Look, are these equations familiar to you? They look rather like the electricity calculation, right? Okay, if you Ohm's law. Recall your memory in Ohm's law, which is used for the calculation of electricity. The current equals to the voltage, the drop of voltage, divided by the resistance. Is there anyone who do not know this equation, Ohm's law? You don't know? You don't know? Oh, okay. If that is case, okay. Oops, what's wrong? Okay, this one, we already rearranged it like this. Right? X2 K2 area. The temperature drop. The temperature difference divided by according to the Ohm's law, if we have an electric circuit, you don't know the Ohm's law. Okay, current equals to the drop of voltage divided by the resistance, the resistor. Through the electric circuit, the current is the same. Okay, the current flows through different resistors. Voltage will drop. Okay, So if we compare this equation for heat conduction, they look quite similar with this equation. So we'd like to apply the electrical analogy method to help us solve this conduction problem. That is, we assume Q dot is assumed to be the current. Delta T, that is the temperature difference, is assumed to be the voltage drop. And then we can have a RH, that is the thermal resistor, similar to this electrical resistor. So according to this equation, this thermal resistor equals to X, the thickness, the thickness divided by the conductivity and the area. Right? We compare this equation to this equation. So what we have is, if we have an electric circuit, we can sketch out this kind of simple diagram to help us solve the current inside this circuit. That is, at this point, we have voltage, V1, and at this point, we have voltage, V4. Here we have three resistors. So we use I, the current, equals to the drop of the voltage divided by a total resistor. Total resistor equals can be simply calculated by the summation of the three resistors. The three resistors can be simply added together to give us this total resistor. That is why we use this analogy method to solve conduction. So, according to the electric circuit, we can draw a similarly heat transfer circuit. At this point, we have temperature T1, let's say a higher temperature. And at this point, we have a lower temperature. So we have three layers, three different material. We can assume they are resistors. First layer, resistor 1. Second layer, resistor 2. The third layer, resistor 3. Inside this circuit, the heat transfer rate is quite similar with this current in this electric circuit. It is the same. Drawing the whole system, drawing the whole process, it is the same. So we can calculate this conductive heat transfer by Q dot equals to the change, the drop of temperature divided by this one is a total thermal resistor. Total thermal resistor. Similar to this electrical calculation. RH total, the total thermal resistor equals should be the sum of the 3 resistor. 就是像是我们算电路的时候，我们会用欧姆定律 Ohm's law for electricity。欧姆定律它的本质其实就是电压 voltage 的 drop divided by the resistors， 我们叫电阻。It gives you the current， 你得到了那个算出来那个电流。You can calculate the current. The voltage drop divided by the resistor. This is the Ohm's law. 然后我们现在有的这个 equation 是非常像这个 Ohm's law 的。我们可以把它这样写一下，是什么呢？其实就是 the drop of temperature divided by these parameters. We can assume it is a thermal resistors. 这样就给了我们一个什么呢？我们可以把它想象成是一个 thermal circuit。那在这里，我有温度是最高的 T1， 它一路流过。本来我们有3个 layer， 3个不同的 material。现在我们把它看作是什么呢 ？resistor， thermal resistor。temperature 从这里流过，它就会怎样降低？然后一直到最后的这里，我们得到了一个最低的温度。这个是一个假设，或者是帮我们去计算。为什么这样子呢？因为我们通常是知道最高温度和最低温度，对不对？但是我们很少说知道，我们不太可能，我们有一个复合材料，我们有3层板，那你没有办法去测量中间的，所以你知道最外面和最里面，我依旧想得到那个 heat transfer rate， 那怎么样呢？那我就需要知道一个 total 的 resistor， 所以用这个假设呢，用这个类比的方法 analogy method， 你就可以用这个去算一个非常简单的，去得到你的这一个 total heat thermal resistor。因为像是在我们算 electricity 的时候，我们是直接简单的可以把这3个 resistor sum 加起来，你就得到一个 total resistor。那你知道这边的 voltage， 这边的 voltage， 你就可以很简单的、很快速的算出来这个 current。同理，同样的道理，对于这个，我们知道 T1， 我们知道 T4。那我们想知道 heat transfer rate， 那要怎么办呢？那其实就是很简单的，我想算出来一个，我不关心你这里面有几层，我最关心的是你总的这个 thermal resistor 是多大。那我从 T1 到 T4 的这个 thermal drop， 这个 temperature difference， 我就可以得到这个 Q dot。所以最重要的事情是我们要算出来这个 RHT，the total thermal resistor， 类比于这个 electric circuit。RHT is the sum of the 3 layer. At this point, any problems? I'm not sure whether you can understand this method. Any problems? In essential, we use this thermal circuit to calculate the the heat transfer rate, because we know the temperature at the starting point and the end point. We know the initial, at the outer surface, the two outer surface, but we cannot measure the temperature inside our layers, right? It's not easy for us to measure. We have maybe a book this. We can measure this side, and we can measure this side, but we cannot measure inside the temperature inside. So what we want to do is to assume this box with different page at a whole system with thermal resistors. So by using this method, we can simply calculate the thermal resistors by the sum of each resistors at this point. Can you understand? If yes, I will continue, okay? So by using this method, we can calculate the, maybe use this, yes, use this one. So this should be R1. This should be R2. This should be R3, right? So for R total, the total thermal resistors equals to, right? So now we can get the heat transfer rate. That should be the delta T, right? If we plug these equations into this one, we can get these equations to calculate the heat transfer rate. In electric circuit, we have two combinations of the resistors. First is resistors in series. So if we'd like to calculate the total resistor or the overall resistor, that is quite simple. The sum of all the resistors. In this case, if we have two resistors in this circuit, RT equals to R1 plus R2. Quite easy, right? The another type is the resistors are arranged in parallel. So if you do not know the Ohm's law, maybe I need to show you here. That should be the current split by these two loops. Here we have I1. Here we have I2. So I1 plus I2 equals I, right? And from here to here, the voltage drop is the same. So I1 equals should be V1 minus V2, right? V1 must make 2. I2 equals V1 minus V2 divided by resistors 2. We plug these two equations into this equation. What we have R1 plus equals V1. So we can get these equations. This is how we can calculate the total resistors of two resistors in parallel. At this point, any problems? If no, I will continue. Is it okay for you? Okay, good. So here we have known the method, the analogy method, the electricity analogy method. So we'd like to apply this electrical analogy method to the pipe, to the cylinder. In this problem, we have a composite cylinders, which has 2 layers. The first two layers with two different material. That means we have 2 different conductivities. At the inner face, it have a temperature T1. At the outer surface, we have a temperature T2. We assume T1 is larger than T2. Okay, this is our problem. So, first, let's sketch out the diagram, the heat transfer circuit diagram. We have T1 at the inner surface. That is T1, the higher temperature. And we have, due to the temperature difference, conduction happens. That means T1 through this green material, this green pipe, this layer, conduction happens. At this point, we have T2. Here should be R1, the resistor R1. Sorry, this should not T2. We should not use T2. Let's say maybe, oh yes, it should be T2, I'm sorry. At the surface T2, yes, this is T2. The middle surface between the inner layer and the outer layer, T2. From T2, from the middle surface to the outer surface, we again have conduction. That should be R2. Finally, we have the temperature at the outer surface. That should be T3. During the whole process, we have the same conduction heat transfer rate. And so if we use RT equals what? RT, the total thermal resistor. Oh, You are so quick. That should be R1. Right? The sum of R1 and R2, the two resistors. So here, in this equation, if we rearrange it, divided by this one should be R, right? For a circular pipe, this is a resistor, the thermal resistor for a circular pipe. So we use this R. That means R1 should be K1. And R2 ln R3 over R2 divided by 2 pi L K2. At this point, any problems? Can you understand? RT is a total resistor, okay? And R1 and R2, we use the equation from here. The equation for a circular pipe. So we plug these two equations into this equation. Finally, we can get two pi LK1 plus 2 pi LK2. And this is our total, right? Total resistor. At this point, any problems? If no, sorry. This is the equations when we applying the electrical analogy to a two-layer cylinder or two-layer pipe. Okay, at this point, you should know how to calculate the conductive heat transfer through multiple layer cylinder or multiple layer plane, okay, slab. If no, let's take a 5-minute break. After the break, let's go through our class tutorial, okay? And if you cannot understand the Ohm's law, this electrical analogy method, please feel free to come to ask me, okay? For those who are facing a computer, any problems? Can you understand this method? Ohm's law and this electrical analogy, okay? 你们没有学过欧姆定律吗？这是我中学时候学的，你们忘了？那需要再给你们解释一下吗？还记得吗？在这里 OK 吗？就是这里，你们中学没有学过吗？那希望我要不一会儿再给你们解释一下。So is there any question for two labs in prep? I want to ask V1 divide the input and So is there a question? Yes, of course, we have the two labs in parallel. We will discuss it later, okay? For the labs in parallel, we will discuss it later. And I want to ask V1 and V2 divided input. V1 and V2 divided input and which page? I'm sorry, I didn't get your point. Is this one? This slide? V1 and V2 should be the voltage. This one, yes. What's wrong? This one, delta V divided by RT. Is this one? 这个是欧姆定律 ，Ohm's law. Recall your memory in Ohm's law. That is the 就是我们在计算 electricity 的时候，我们在计算这个电路，我们叫做电路的时候，计算这个 I， 这是 current 嘛 ，current equals to the drop of voltage divided by the resistors， 那就是电压除以电阻，这里吧。我给你们写一下，在这里。I equals delta V divided by the OK， 是 the voltage 的 difference divided by the total resistor。其实在这里呢，我应该一会儿上课之后我再给你们讲一下这里吧。我感觉你们可能真的都已经忘了。V 等于 IR。Yes, V equals to IR. This is the Ohm's law, right? It's potential difference. Potential difference. Yes. Yes. Potential difference. Yes. Yes. Potential difference. The voltage difference.我在这里插入一页 PPT 吧，这样子。Heat transfer, yes, heat transfer. To be honest, during my study in thermodynamics, engineering thermodynamics, I didn't learn the heat transfer. Actually, we have another subject that is heat transfer. we have two different subjects, heat transfer and thermodynamics and fluid mechanics. But here I'm not sure whether in this college combine this together.
They got another course called heat transfer.
Yes, you
Level 4.
level. Oh, so this is a basic.
Yes, this is
yeah.
introduction.
Oh, introduction part. Okay. Actually, we take two courses. Because heat transfer is quite, actually here 就在这里给你们讲的是非常非常简单的。事实上，我们学 mass and heat transfer 的时候，我们都是做那个偏微分方程那种，就有点像流体力学的那种，就要解边界层啊，还有那些的，比较很复杂。哦，所以我当时看的这个其实还是很疑惑的，因为这个对我们来说，就是所有的这些都是 1 hour 的，就是一个 introduction 这样子的。可能你们会在你们 level 4的 heat transfer 会学的会就难一些，对。因为我们的 thermodynamics 就到就是 cycle 啊 combustion 那些的就没有 heat transfer 的。哦。那我懂了，你们为什么要学这？因为我们对于当时我上大学的时候，我的 undergraduate 那是必修课，那就是我必须要修的课。fluid mechanics，thermodynamics， we call it engineering thermodynamics and mass and heat transfer and aerodynamics. Actually, thermodynamics, heat transfer, and fluid mechanics, we usually call it a triangle. Fluid mechanics, thermodynamics, and heat transfer. Okay, let's make a start again. Some students feel confused with almost low, and you may forget about this. So I may explain more about in this almost low. See, this is our electric circuit, right? So what we have is I drawing the whole process, drawing the whole circuit is the same. That should what we have is V2. Oh, sorry. V1 minus V2 over R1 equals right? Because the current is the same, drawing the whole circuit, right? So we use that is the change or the voltage over the total resistor. Here, the total resistor can be simply calculated as the summation of the three resistors. Quite easy and straightforward. That's why we use this electrical analogy method to our heat conduction calculation. This is resistors which are arranged in series. If we arrange it in parallel, V1, let's say V2. Okay, here we have R1 and R2. The current is divided by this two circuit. That should be I1, this I2. So, right, the voltage drop, the change of voltage should be same to both R1 and R2. So, I1 equals V1, I2 equals V1 minus V2. Plug it into this equation. Oh, what is I? V1 minus V2 are total, right? So we can get the relationship in parallel. By using this equation, we can calculate the total resistor of the two parallel resistors. Okay, so this is how we calculate the electrical circuit by using the Ohm's law. So we try to simplify our calculation in conduction. So we use a similar way to solve our thermal problem, our heat transfer circuit. That is, we assume we have thermal resistors in series or in parallel, so that we can use a similar way to calculate the total thermal resistor. Okay. So please recall your memory. Your 遥远的对于欧姆定律的 Ohm's law 的记忆。Okay. Please recall your memory. Okay. This is our class tutorial. Actually, I rearranged the class tutorial should be 23 or 22 and 23. Okay, I rearranged a little bit. So actually it's the same. I just rearranged the order. So let's solve this problem first. First, we assume a one-dimensional steady-state thermal system. Here, pay attention, one-dimensional and steady-state. Between two different temperatures with negligible radiation. And temperature, we assume T1 is larger than T2. So we consider a four rectangular box with a thickness of 4 meters. Should be, you may say less, okay, 4 meters. And we know the thermal conductivities of these 4 different materials. So we'd like to determine the overall thermal resistance. And then we'd like to calculate the heat transfer rate. If T1 equals to 80 degrees C and T2 equals to 30 degrees C. So first thing, try to draw the diagram, sketch out the simple diagram for the heat transfer circuit. So what we have is, we have T1 at this surface. So we have the conduction through the material A. So this is RA, right? And B and C, wall A and wall B and C, that is in parallel. Okay, parallel. So this is RB. This should be RC. Again, the conduction through the material of wall B. Finally, we get the temperature at this outer surface should be T2. T2. Along this circuit, since the temperature T1 is larger than T2, the direction should be in this direction from T1 to T2, right? Along this circuit, the heat transfer rate is the same. Okay? So let's calculate. We'd like to evaluate the overall thermal resistance. That should be RT, right? Equals RA. Here, B and C. RB and RC are in parallel. So what we have is here has a RBC, right? So we need to calculate RA and RBC and RD. Here, RBC, remember the relationship? Right? The relationship in parallel. So now we need to calculate RA, RB, RC, and RD. RA, for conduction, the thermal resistor equals to XA divided by Ka, the conductivity times the area, right? XA equals to what? XA should be 0.1 meter. So 0.1. Ka is our known values. Area of material A should be times 4, right? Is okay? This area. Use times 4. This one. Okay? So guys, what's the number? Come on. Good. K per watt. K per watt. Because we have X in the unit of meter, Ka in the unit of K should be use this one, maybe better this one. Yes. Because we have the watt, right? And we have the meter times meter square, right? So for the resistor, the unit should be K over watt. Okay? This is the unit. Okay. RA. RB equals to XP divided by KB, the conductivity of material B, times the area of material B. XB is 0.5 meter, right? 0.5 meter. The area, the KB is 0.6. Area should be what? How to calculate the area for material B? Who can tell me the area? Sorry, can you speak louder? 4 times 1 0.2, right? Because B, the height should be 1.2, right? So the number should be 0.005 K over watt. Okay, this is RB. RC, how we calculate RC? XC divided by KC and area of material C. KC is a conductivity of material C. So what we have is, again, the distance is 0.15 meter. KC is 0.8. Area 4 times 1, right? Remember, you should remember the area is the area normal to the heat transfer direction. So it should be in this direction, right? In YZ plane. That is 0.00469 K per watt. And for RD, XD divided by KD and AD, the area of material D. XD equals to 0.12. KD is 2. Area, again, 2.2 times 4. Okay, what's the number? What's the number? Who can tell me the result? What's the number? Zero point 0.068 K per watt, right? So we need to calculate the RBC, RBC by using this equation. That is RBC equals 1 over, right? So that should be okay. Please calculate this number. This result. What's the result? What's the result? Can you follow? Can you follow? Yes? Good. That should be 0.0 K per watt. Right? Oh, sorry. Is it right? Is that right? Yes, I think it's right. Okay. So for R total, the total thermal resistor equals RA plus RBC plus RD. That should be plus. Okay, what's the result? Zero 0.3 1 2 5. No zero. Is the result right? This one, right? Right? Yes. What? Okay, this RT. This is the overall thermal resistance. Can you follow? Good. I need a new slide. Now we know the number for the total resistor. We know RT. We'd like to calculate the conduction heat transfer rate. We know the temperature difference. We know the total resistors. So Q12, the conductive heat transfer rate equals to delta T over by the total thermal resistor, right? Delta T, the temperature drop, the temperature differential should be T1 minus T2, right? That should be so. What's the result? Conduction heat transfer rate. Conduction heat transfer rate. Good. Follow? That's how we calculate the thermal overall, the total thermal resistance by using the electrical analogy method. Okay, at this point, you should know how to calculate the overall thermal resistance and as well as the heat transfer rate by using this overall thermal resistor. Okay? Up to now, any problems? Can you follow? If no, I will continue. Based on what we learned, we add more. We add the convection boundaries into our conduction system. So first thing, how to calculate the convection heat transfer. Recall your memory in Newton's law of cooling. This is a basic equations to solve convection heat transfer. Recall your memory. I told you that convection is a heat transfer from a heat surface to its surrounding flow, or from a hot fluid to its surrounding surface, right? Either from the fluid to the surface or from the surface to the flow. When we talk about the convection, definitely convection involves fluid, the moving fluid, as well as the interface of fluid and solid. That is convection. Therefore, convection combines the mass and the heat transfer because we have the movement of fluid. So we use Newton's law of cooling to calculate the convective heat transfer. That is, the convection heat transfer equals the heat transfer coefficient times the surface area, which is normal to the heat transfer, and times the difference of the water temperature and the fluid temperature. This is a basic equations to calculate convection. Here you should pay attention H, the heat transfer coefficient for convection. It's not the same as K, conductivity. I told you K, conductivity, is a material property. It is property of a material, but H is not a property of material. So it is quite difficult to solve the convection problems because H is difficult to solve. But here, we use H as a constant to solve simple problems. In the next lecture, I will introduce to you how we find the real heat transfer coefficient. But at this point, you should keep in your mind, H is not a property of material, okay? So now we add convection boundaries to our conduction system. That is, we have again a solid plate, a solid slab, which is located between two different fluids. Fluid A with a higher temperature and fluid B with a lower temperature. So what would be happen is that convection happens from fluid A to the surface to this surface. Well, convection happens from this surface to fluid B. So we have a temperature difference at the two surfaces. Definitely, conduction through this wall will happen. That is, we have convection boundaries in this conduction system. Convection from fluid A to this surface, well, convection from this surface to fluid B. Two convection boundaries. Due to the temperature difference, we also have the conduction through this wall, this solid. That is fluid, solid, and fluid. So first thing, we need to introduce the Newton's law of cooling for convection. That is the equation in last slide. QC, the convection heat transfer, equals to H, the heat transfer coefficient, times the area, and times the difference of temperature. So again, we'd like to use the electrical analogy to help us solve this problem, to make the calculation easier. Now we apply the electrical analogy. That is, we rearrange this equation. Right? Again, was this This is delta T, the temperature difference. Recall your memory, I equals delta V over R, right? And Q equals delta T equals, over RT. Sorry, RH should be the thermal resistance. So what we have is RH for convection equals 1 over H times A. This is the thermal resistor for convection. In this problem, what we have first, convection from fluid A at temperature TA. Now we can use this equation, that is Q dot equals TA minus T1. Convection from fluid A to our surface, the surface of a solid, because TA is larger than T1. So here we use TA minus T1, okay? Because the direction is from the fluid A to the surface, okay? So HA times area, okay? And then through this wall, due to the temperature difference, conduction happens. So recall your memory, that should be what? Who can tell me? T1 minus T2 over X, yes, good, K times area, right? This part, convection from the surface to the fluid B. So that is T2 minus TB, H, this one, B times area. Here, note that area is constant. Area is constant for this problem. Again, we can sketch out the circuit. At this point, sorry. Should be TA, right? At this end, we have TB. In the middle, we have the first thermal resistor for the convection from fluid A to the surface. Let's say it should be this. It should be HA times A, right? This one. Then we have the conduction heat thermal resistor, should be this one, right? The last one is the convection from the surface to the fluid B. This is a thermal resistor, the thermal resistance for this resistor. So at here, what we have is T1. Here is T2, right? At this point, any problems? So this should be X times Ka. This should be 1 over HBA. So the total thermal resistance should be what? The sum of these three. right? Can you follow? Yes, good. So now we can calculate the heat transfer by TA minus TB RT, right? Plug this equation to this equation. You can get this equation. You can get the heat transfer at this one steady state conduction system with convection boundaries. At this point, any problems? For those who are facing your computers, any problems? No, no problems? Okay. Okay, then let's continue. Next, the circular pipe is quite common in our life. We have a circular pipe. Inside this pipe, we have maybe water, maybe other fluid flows through this pipe. And this pipe is explode to the air, right? Another type of fluid. So in this problem, inside this pipe is fluid A with a temperature at TA, maybe a higher temperature. We use this pipe to deliver hot water, maybe hot water. This should be hot water. And outside the pipe, the outer surface is located at fluid B, inside fluid B, maybe air, have a lower temperature. What will happen is that we have convection from this hot water into our pipe. This should be a convection. And the convection from the pipe to the air, to the fluid B at a lower temperature. Due to the temperature difference, definitely the pipe, the wall pipe, have conduction through the solid wall of the pipe. That is convection from fluid A to the pipe, the conduction through the wall of the pipe, and again, convection from the pipe, the outer surface, to the fluid B. This is the conduction system with, again, two convection boundaries. Let's assume the length of the tube is L. So again, we'd like to use the electrical analogy method. That is EQ dot equals, this is Newton's law of cooling, right? But here you should pay attention. The area is no longer constant. The area is changing. It should be 2 pi r times L. This is a normal area. It is changing. It is no longer constant. So if we rearrange this equation, we plug this term into this equation, we can get right? So for this kind of problem, the thermal resistor, the thermal resistant equals to, right? This one should be thermal resistance, right? Now, let's look at our problems. It is a one-dimensional steady state. So the heat transfer rate is the same through the whole process, right? So Q dot equals to, from here, convection from fluid A to the surface of here inside the pipe. The convection from the hot fluid to this cooler pipe, cooler solid, should be equals to TA minus T1. Pi should be R1 LH, right? This is a convection inside our pipe. Conduction, the wall of the pipe. For that, who can tell me? T1 minus T2 divided by ln, right? This is a conduction through the wall. It also equals to the convection from this outer surface of the pipe to the fluid B. So T2 minus TB, the change of temperature divided by the thermal resistor, that should be R2 LH. Here should be HB, sorry, here should be HA, right? Okay. At this point, any problems? Any problems? Again, we can draw the diagram, the simple diagram for our heat transfer circuits. That should be, here we have TA, here we have TB, right? This should be the convection heat transfer and the conduction heat transfer, and again, convection heat transfer, right? For the thermal resistor, this one should be this. This one should be the conduction resistor. This is a convection resistor. So RT is the sum of these three. The sum of these three. Now we can calculate the transfer rate. It should equal to the TA minus TB. That is temperature differential divided by RT. So you can get this equation. This is the total or the overall thermal resistor for this problem. At this point, any problems? Oops. There is an error in this slide. Who can tell me? There is something wrong in the equation. Which one? Who can tell me? This one. Oops, where's my pen? This one, right? Should be T1 minus T2. Right? T1 minus T2. Good, very good. Okay, up to now, any problems? Can you follow? Up to now, any problems? If no, let's continue. So in general, the heat transfer of the conduction, and the convection system can be calculated from the heat transfer circuit. That is, the heat transfer rate equals the temperature differential divided by the total or the overall resistance. Overall resistance. If we use the equation, we rearrange it. We use U times area and times the temperature difference. That is RH equals to 1 over U times A. Here, we sometimes call U as the overall heat transfer coefficient. Okay, in general, we can solve this problem by using this equation. That is temperature difference divided by overall thermal resistance. Okay. If it's okay for you, let's continue one more class tutorial. Okay. As I said, I just rearranged the question 22 and 23. Actually, they are the same. Okay. So here, what we have is, again, we assume the one-dimensional steady-state thermal system between the two temperatures with negligible radiation. We assume T1 is larger than T2. In this problem, we have two circular pipes with two different materials. And inside the pipe, we have a fluid. And outside the pipe, we also have another type of fluid. So, we'd like to determine the overall thermal resistance. And we'd like to calculate the heat transfer rate if we know the value of T1 and T2. That is the value of the two fluids, the temperature value of the two fluids, fluid A and fluid 2. Then we'd like to determine the temperature at the external surface of the circular pipe. That should be this one, right? Yes, the external surface here. We'd like to know the temperature at here, the outer surface. So first, sketch out the circuit, the heat transfer circuit, to help us with this problem. That is, we know T1 and T2, right? So what we have is convection from fluid 1 to this surface. Let's say it should be R1. And then conduction through pipe A, conduction through the wall of pipe A. Let's say the resistor is RA. And here, pipe B, again, the conduction through the wall of pipe B. This is a conduction through pipe A, conduction through pipe B. So we have the resistor RB. From B, the outer surface of B, we have the convection to fluid 2. That is R2, the convective thermal resistor. Finally, we have temperature T2. Temperature T2. Again, inside this circuit, we have the constant heat transfer rate Q dot 1 to 2. Okay, so but here we have TA, and here the middle surface of TA and B here should be TB, right? We'd like to calculate the value of TB, right? That's the diagram. Is that right? Not right. Let me check. I think something wrong. R1, yeah, it's okay. Yes, good. Good. R1, let's write the null values. R1 equals to 0.1 meter, right? R2 equals 0.2 meter. And RAB at the middle surface of A and pipe A and B equals to 0.12 meter, right? Okay. Up to now, any problems? If no, let's continue. Determine the overall thermal resistance. So we need to calculate each thermal resistance and calculate the sum of all the 4 thermal resistors. So first, R1 equals what? This is a convection from the fluid A to surface to pipe A, right? The surface A. That should be 1 over H1, right? 2 pi R1L, right? Okay, good, very good. This is R1. Right, what's the number? H2 to A should be 16. Yes, 16. And 5 is the length of the pipe. And 0.1 is the radius of this inner surface. Okay, so the number should be 0 K per watt. Okay, so R2, the convection at the outer surface of the pipe. Convection here. So R2 equals to what? 1 H2, 2 pi R2. Yes, good. L, very good. That should be 2 pi, should be 0.2 and 5 times, this should be 9. What's the number? Should be K per watt. Okay. Okay. This is a 2 convective heat resistor, thermal resistor. Now let's calculate RA and RB. RA equals to what? RA ln RAB over R1. RAB over R1. Okay? Times 2 pi L Ka. This is RB. Any problems? Ln RB over R1 divided by 2 pi L times the conductivity. So that should be ln 2 pi 5 should be 2.2. Hello, what's the number? Please help me calculate this number, okay? I don't have a calculator. So what's the number? What's the number? Okay, what's the number? Okay. Good. K per watt, right? RB. Who can tell me how to calculate RB? R2 over, yes, good. Pay attention here, should R2 over RAB. Okay, RAB, R2 over RAB. 2 pi L, the conductivity of, B, pipe B. That is ln 2 pi 5 KB is 0.3. The number should be K per watt. At this point, any problems? To anyone? What's wrong? No? No problem? For those who are facing computers, can you follow? Can you follow the class tutorial, the calculation? What's wrong? Good. You give me a good number. Thank you. So, if no problem, let's continue. Question A. We'd like to calculate the overall thermal resistance, the total thermal resistance. That should be the sum of all the 4 resistors. That should be R1 plus RA plus RB plus R2, right? What's the number? B. K per watt. Okay. Very easy, right? The sum of these 4 resistors. We can get the total thermal resistance. Question B. Heat transfer rate. Who can tell me how to calculate Q dot 122? The equation should be delta T over RT, right? Delta T should be T1 minus T2. T1 minus T2 divided by the total thermal resistance. That should be 50 divided by. So what's the number? What's the number for this question? What's the result? Hello, what's the result? Good, very good. That should be Very good. That should be change to black ink. Watt. That is a heat transfer rate for this system. This convection, conduction, and convection system. The last question is that we'd like to determine the temperature at the external surface, at the outer surface. That should be the TB, right? The surface, the temperature at the outer surface of pipe B. That should be TB. So we can just have a look at this part. Because the Q dot is the same during the whole process, right? So what we can do is this is T2 and this is TB. We have Q for this circuit. We just look at this part, right? By using Q dot is constant through the whole circuit, so that we can get TB minus T2 over R2, right? Ohm's law. Ohm's law. Remember the Ohm's law? So we know the value of Q dot. That should be, if we arrange our problem, the equation, we can get the temperature at the outer surface. What's the number? Sorry, it should be 0. Who can tell me this value? What's the number? I do not have a calculator, so please help me. No one knows? 3，我听到一个3。I heard 3. 3. Sorry, 3 0 0 6. Okay. Degree C. Thank you. Okay. Done for this equation. So you should know at this point, you should know how to calculate the overall thermal resistance for this convection, conduction, convection system. In other words, the conduction system with 2 convection boundaries. According to the calculated overall thermal resistance, you should be able to calculate the heat transfer rate through the whole system. Because we have the one-dimensional steady state assumption, so the heat transfer rate is constant through the whole system. Again, you know the heat transfer rate. That means you can calculate, you can obtain the temperature at each surface, inner surface, the middle surface, or the outer surface. At this point, you should be able to do this to solve this problem. You should be able to solve this problem. Okay. Okay, another tutorial. That should be the tutorial, the class tutorial question 24. We have a composite wall as shown here, which consists 4 walls with different material A, B, C, and D. They have the same radius. And heat is transferred by convection at both outer surface with fluid I and fluid 2. So we have the convection, conduction, and the convection system. We'd like to estimate the heat transfer rate from fluid A to fluid 2. No, sorry, fluid I, fluid 1 to fluid 2 through a unit radius of the wall. Let's say 1 meter. By the assumption of one-dimensional steady-state conduction through this composite wall, and we also ignore the radiation. We know the thermal conductivities of these wall materials, and here we give you the convective heat transfer coefficient. So let's solve this problem. First, draw the simple diagram again, right? Sketch out the circuit, the heat transfer circuit. That is, here, what we should do first. The parameter, the dimensions for the material for the wall is in cm, right? We need to change the unit into meter, okay? So that is the height of B should be 1 meter. For wall C, that should be 1.8 meter, while the distance along the x direction should be 0.15 meter, while this for D, wall D should be 0.06 meter. Okay, first you need to change the unit into meter. Okay, from cm to m. So first thing, let's draw the diagram. First, from fluid A to the surface, to this outer surface, that is R1. Let's see R1, the convective thermal resistor. Now we have the conduction through the wall A, that is the thermal resistor RA. And what we have here is we have a parallel arrangement of wall B and C. So we have the resistor RB and RC in parallel, okay? At wall D, that is again thermal resistors for conduction. From the outer surface of D to the fluid 2, that is a convective heat transfer R2. Now what we have is T2. Here is the T1 is a higher temperature at 100 degrees C, and T2 equals to 20 degrees C. Okay, this is our diagram. This is our simple diagram to help us solve this problem. Okay, so first, we'd like to calculate the heat transfer rate. Heat transfer rate through the whole system should be the same, should be constant. That is Q1 122 dot equals what? The temperature difference divided by the total thermal or the overall thermal resistance. That is T1 minus T2 divided by RT, the total thermal resistance. Okay. So RT here equals to R1 plus RA. Here, the parallel arrangement of B and C was this. Should be equal to a resistor of RBC. So plus RD and R2. So the problem now become into that we need to calculate the each thermal resistor, right? So let's begin. That is R1. R1 equals to what? Who can tell me? Convective thermal resistor, right? 1 over HA1, right? Good, very good. So that is 1 over H1 is here. 13 area should be 2.8 times 1 unit less. The less is unit, that is 1 meter, right? In this direction. This is area. So we have 0 K per watt, right? So R2 equals to what? R2, the convection at this surface. Convection from this outer surface to 42. The convective thermal resistor equals to what? 1 over H2 times A2. Good. That should be, the H2 should be 8. Yes, 8. The area, the same, right? What's the number? What's the number? Who can tell me what's the number? Should be 0.0446 K per watt, right? This is R1 and R2, our two convective heat, the thermal resistor, right? RA. How to calculate RA? XA. Yes. Ka times the area. Xa equals to 0.1. Ka is 0.7. And area of wall A should be, yes, good. What's the number? .051 K per watt. Okay. So RB. XB divided by KB and the area of wall B. XB is equal to 0.5. KB is 1.6. Area of B, area of wall B should be 1 times 1. Yes, good. What's the number? It should be 0, K per watt. Okay, that is RB. RC. Again, XC times over KC times area of wall C. XC is 0.15. KC is 1.1. Area should be 1.8 times 1. Right? So the value should be 0, 0. Sorry, it should be K per watt. And RD equals XD over KD times area of D is quite simple, right? 0.6 divided by the 0.5 times, right? The number should be K per watt, right? So this, now we have known this, the values for each thermal resistor. Now we can calculate the RBC based on RB and RC. Recall your memory the relationship between the RBC and RB and RC. The resistors in parallel, that should be 1 over RBC equals 1 over RB. You should remember this equation, okay? You should remember these relationships to solve problem. So by using the value of RB and RC, we can calculate the RBC as 1 over So what's the number? What's the number for RBC? Who can tell me? For those who are facing your computer, can you tell me? Good. You give me the value. TB minus T2. Which one TB? This one? Okay, let's finish this first. Very good. Very good. Oh, change it to 0.0419. Very good. So we can calculate the overall thermal resistance. That should be the sum of all the thermal resistors. That is the plus the value should be K per watt. So now we can calculate the Q dot 1 to 2. The heat transfer rate equals to what? Delta T RT should be T1 minus T2 RT. Okay, the final value. For good. Very Very good. Now solved. I see a message you say that's a previous one. This one. Is this one? This one. The Q1.2 should T be minus T2. Here should T be minus T2 because is a drop of the temperature difference. The larger temperature minus the lower temperature. Okay, so should be TB minus T2. Okay, but nose is different. Nose is different. The solution of Professor Liang or no, the PPT. This one. Sorry, I didn't get your point. Is this one? PPT? No. Previous. I'm sorry, I didn't get your point. Is this slide? Any problem? Do you know what? Yes, the slide roll up. Roll up. This one. Page 20. Yeah. Yes, I have already told you. This one is wrong. Should T1 minus T2. Okay? Yes. Tutorial 的题目跟 PPT 事实上它们是一样的，我只是把它们 rearrange 了一下 ，OK？ Should T1 minus T2, OK? Oh, this one should you say, oh, I know what you mean. This one, right? This is T2 minus TB. It's okay. This one is wrong. It's true. T1 minus T2. Okay. High temperature to 对啊，这 high temperature to low temperature。等一下 ，B 是哪个？对啊，TB 更小嘛 ，TB 小于 T2嘛，所以就是 high temperature minus the low temperature， 所以是 T2 minus TB， 没有问题，这里没有问题。说 Professor 梁这里有问题吗？我看一下，好像 Professor 梁那里好像是有点问题，是不是？他是不是写错了？这里吗 ？T2 应该是 TB 减去 TB minus T2。You always use a higher value, higher temperature minus the lower temperature, okay? If not, that's wrong, okay? How can I close this? Okay, it's okay, okay. Okay. Oops. Okay, that's all for today. Any problems? Okay, no, good. So always remember use a higher temperature minus the lower temperature, especially in the electricity analogy method. Okay, you use a drop, voltage drop, temperature drop. Okay. Okay, guys, girls, if you 如果你忘了 almost low, okay, 回去 recall 一下 your memory in almost low, okay. Try to understand the method behind, okay. I will save this PPT file with handwriting and upload it into Moodle. You can check it, okay. About the test in the next week. Any problems? May I ask what format? MC. How many questions? Sorry, I don't know. 是 Professor 梁 prepare 的那个 test paper。我记得他跟我讲过是 MC 应该是 MC， 但是具体的 how many questions? I'm sorry, I don't know. I didn't see up to now. I haven't seen the test paper. Okay, thank you guys. If you have any problem, please feel free to ask. And 我先结束一下 recording. Stop recording.